if r is bigger than 1. Okay, so now Willie was asking, well, what would the notion of a closed ball be? What are the closed balls if r is, let's say, a half? The open ball is just a single point x. The closed ball is just a single point x. That's correct. So they are the same thing in this weird space. Okay? It's not so weird, actually, because the discrete metric is really, it's a very natural metric. Just tell me if two things are different. Okay? This is the metric that perhaps be most useful to a computer scientist. Tell me if two things are different. Okay. Great. So we have this notion of balls, and now we can define what it means to be a limit point. Now, of course, the motivation here is to give me some sense of when a certain set of points is getting close to another set of points, right? So the question we might ask is, when does a set, let's say E, if you like, approach, in quotes here, because I haven't defined this, I'm just saying, approach a point X. That's sort of the question, right? Or point P. Let's use the letter P. Okay? So, you might have a couple of different pictures in your head. One picture might look like this. Give me a bunch of points like this, right? And then there's like, these things seem to be approaching this point, P. And these might be some points in the set E. But it doesn't have to look as discrete as this, right? It could look like this. It might be that, you have just basically a set like this. And you have a point P right on the boundary, right? Or a point P inside, right? I mean, certainly, if you're inside this set, you can find a bunch of points that somehow approach this one point P. With me? So how would we, being mathematicians, how would we define a concept that would capture this idea? And that's the concept of a limit point. Okay, so here's the definition we ended last time with. So if you have a point, let's say P, in some big metric space X, from now on, all spaces will be metric spaces, unless I otherwise say. Okay? You have a point P in some space X, we'll say is a limit point of a set E if every neighborhood, did I say some neighborhood? No. I said every neighborhood of P contains a point Q in E, where Q is not the original point P. Okay? So in other words, it contains some other point Q that isn't P. Hugely important definition. It has to be true for every neighborhood of P. That is, every ball around P. Okay? So let me do a couple examples here, and these will actually be our running examples. In fact, since I'm going to use these examples a lot, I'm just going to put them on this board here. In your notes, you could still put it there, but I'm going to put it to the side here because we'll work for this on this board quite a bit. So here's one example in R. Suppose I have the set G, which is a set of all 1 over n, such that n is in Z. N is in, let's say, the natural numbers n. Take a look at that set. An example, this picture would look something like this. Let's mark it with a bunch of points here. Here's 1, and this is 0. And this is the set of all reciprocals, isn't it? a half, a third, a quarter, a fifth, etc. Okay? Everybody happy with this picture? Okay, so here's a question for you. For this example, are there any limit points of this set G, which is the green points? Yes? Where? 0 is a limit point. Excellent. Let's mark it here. The claim is 0 is a limit point. Okay. Why would 0 be a limit point? What's the justification? Well, it better be true that every ball around 0 contains a green point. Is that true? What's a ball look like in R? Good. A neighborhood, so let's just mention that. Notice that neighborhoods of P look like P minus epsilon, P plus epsilon for some epsilon. You know, so they're like some interval around P of some radius, right? So in this picture, what do we have? Here is one such ball. It looks like this. Will any such ball contain a green point? Yes. So 0 is a limit point. Very good. Oh, okay. Let's do another example. Here's another example. This is in R2. I'm going to describe a set B. Consider the set B. And I'm just going to draw this picture in the plane, if that's okay. So the picture, it doesn't even matter if I have axes here. I'm just going to draw. Here, forget the axes, because it just clutters up the picture. Here's what I'm going to do. Here's a set B, okay? How about this? So I'm going to be consistent here and make these green. The sets are green. There. There's a point here. There's a point here, okay? There is a set here, which kind of looks like a rectangle. And I'm dotting the top, which basically means don't include the points on the boundary here. And then I'm making these solid, which means include those points. Okay? And I'm going to let the set be everything inside as well. Happy? Okay. Happy? Okay. And then let's give this thing, I don't know, let's add another little set here. How about this? Okay. And now let's include everything inside except for one little point that's missing. Okay? So this is really hard to see, but there's a point I've taken out. So this is a disk not containing its boundary with a point missing. Okay, so there's a point missing. Okay? Everybody happy with that? Okay, so let me label some points here. Let's call this point A. Let's call the point missing out of the nose there B. It's like a little nostril, if you like. Let's call a point on the boundary here C, a point here D, and a point here E. And let's place some point outside this picture. Let's call this point Z. Okay, question. Which of these points, these labeled points, are limit points of the set B, which is the green points? Which points are limit points according to the definition? Take a second to discuss it with your neighbor. Which points are limit points? Okay, question. Is E a limit point? Everybody, I want everybody to answer. Yes, it is. Okay, because any open set, any